Evet. Buyurun.
Okay, welcome back. Now we will proceed with the regular sessions. And each presenter will have 12 minutes for the talk, and you will have 3 minutes for the questions. And I'm going to warn you about 1 minute before the talk finishes. Okay. So now we can start with our first presentation. The first presentation will be held by Mehmet Can Türkeş, Nuri Erdoğan, and Yiğit Berkay Uslu. They are students from Boğaziçi University, and today they will talk on hot-end quality control and process monitoring for glass packaging production using SWIR imaging. The stage is yours. You can start.
Thank you, Professor. Good morning, everyone. My name is Berkay Uslu, and my fellow teammates are Mehmet Can and Nuri Erdoğan. Today, we'd like to present to you our project on hot-end quality control for glass packaging production using shortwave infrared imaging. So I will start with some terminology and our problem definition. A typical glass production process consists of two main stages called hot end, as you can see here, and cold end stage. The hot end stage refers to melting and glass forming stages combined, and is followed by the cold end stage where the newly formed glass products are annealed and left to cooling. These stages are illustrated, as you can see here. And elaborate and detailed quality inspections and quality controls are generally performed at the end of the cold end stage here, since the products have long taken up their final form by that time. However, there's a considerably long amount of time between when the first glass is first formed and when the quality inspection actually takes place. This, in turn, significantly reduces the effectiveness of, let's say, determining the root causes of errors and prevents the process operators from taking remedial action, if needed, in a timely manner. So by moving quality control and inspection stage to the hot end stage, we can not only avoid update rate insufficiency and defect propagation, but also reduce the carbon footprint of the factory, since if there is an error, less products will be dumped in a shorter amount of time. As such, transfer of quality control methodologies from cold end back to hot end is a great challenge due to introduction of different environmental conditions and difficulties, some of which are specific to the hot end stage. To name just one of those challenges, we can say the high ambient temperature close to the production machine, the IS machine, severely limits the effectiveness of conventional cold end inspection methodologies using image processing techniques. Although there are a few hot end quality control monitoring solutions that are commercially available, the image processing aspects of such products remain academically an open problem due to strict protection of industrial intellectual properties. And in our project, we address the image processing problems at the hot end quality control and aim to develop a quality monitoring, enabling timely corrective action. The access to production facility is provided by a glass packaging production factory in Turkey, whose name is kept private in this presentation upon their special request. So here you can see a system diagram. The quality control and monitoring system we consider employs a shortwave infrared imaging line scan camera, which faces the products moving on the conveyor belt. The camera captures radiations and reflections in the SVIR band, and each frame we capture consists of 512 consecutive line scans, each having about 1024 pixels. The line sampling rate of the camera is continuously adjusted so as to track the production rate through a programmable logic controller or PLC connection, so that we can have a smooth and uniform aspect ratio for all products through a single campaign. To mitigate the possible signal-to-noise ratio degradation or SNR degradation that might be caused by the ambient temperature, we use chillers to cool down the cameras. The image processing module we developed is supposed to detect the products, apply segmentation, and then retrieve the contours in an accurate manner with high accuracy in a short period of time, about 175 milliseconds for each product on average. This is one of the important real-time constraints on our project. And following the accurate retrieval of the counters, we can apply shape and intensity-based defect analysis to achieve the quality control and defect detection. So in this slide, I present you some of the defects and anomalies that typically occur during production. For example, on the left, you can see a production defect that is appropriately called a freak product. Also here, you can see a hot spot where we have extreme hot lines on the product going from top to bottom. We also have an intensity asymmetry here, for instance. And for instance, to the rightmost figure, we have a fallen product. These are some of the typical problems. And we would like to emphasize that in this project, we tackle the challenges beginning from frame capture all the way to product contour obtainment. And we leave the discussion of how these defects can be detected to a future work. So the first submodule in our system is tasked with frame capture and product localization. Here you see the products moving on the conveyor belt. We capture the frames. And recall that the images we read are read one line at a time by the line scan camera. To obtain a full frame, we combine the continuous stream of 512 line scans. As you can see to the figure, the lower left side of the slideshow, it's a common occurrence that in that case, a product may stride over 2 consecutive frames. Therefore, we append the last 2 frames so as to obtain an appended frame. This new frame, like I said, is called an appended frame, and our segmentation methods work on this appended frame. And now that we have obtained the appended frame, we wish to obtain a rectangular bounding box as shown here. Here, the bounding box is dictated by the 4 offsets given by the top offset, the bottom offset, and the start and end indices. The lower and the upper edges of the bounding box, which in that case would be these 2 edges, are determined with the aid of projection followed by Otsu thresholding. In particular, the intensities are projected onto the axis perpendicular to the radial axis of the products. So in this case, like you see in the middle figure, we project the intensities to the horizontal axis, and then we have such a distribution. And then using this vector, we can apply thresholding to obtain the optimal value, which dictates where these products start and end. And the other 2 edges, or the margins, top and bottom margins, are assumed to be constant throughout the campaign. And we assume this information is readily available with the input of the process operator prior to production. And we find great use in expanding the bounded products by 75 pixels, about 75 pixels in all directions. This enables us to capture more background and increase the contrast from which the segmentation methods we will discuss, such as watershed segmentation, benefit greatly. These expanded localized product images are appropriately called extended localized product images, and we abbreviate them as ELP images. A typical ELP image is shown here, as you can see. Now we're done with frame capture and localization submodule. My teammate Nuri will pick up from where I left off.
Thank you. After successfully obtaining the localized images, we may now proceed to the segmentation part, where the aim is to obtain a binary mask image, like the image on the right. As it can be seen from the GIF, some of the bright regions appear at different locations for each product, and depending on its orientation on the conveyor belt and the current temperature, which changes the SNR around the image. Therefore, we cannot simply create a ground truth mask and match it with the input images. We have to find a robust binary segmenter that works irrespective of the ground truth shape. And the first challenge is that, as Berkay said, we have a limited time per product for localization, segmentation, and analysis functions for all. And since the machine sends approximately 6 products per second. And in order to achieve this, we look to binary thresholding methods, where the algorithms try to find the optimal threshold without resting upon any iterative methods like slick or region growing. Instead, the methods like Kittler and Otsu gave very promising results under certain modifications. And so, like here we can see the histogram and 3D visualization of the product. On contrary to what Otsu needs for best performance, the histogram does not have a bimodal distribution. So the background dominates the image, and hence Otsu finds a higher threshold than desired. And as a solution, we propose to take equal number of background and foreground samples, which is called region sampling, as shown with rectangles here. And under this set, the pixel distribution changes to figure as shown. And as seen, two Gaussians are now clearly visible, and background-foreground separation can be done by Otsu. And secondly, in order to detect the most darker regions around the neck, we applied another Otsu on the upper half of the image. And by another Otsu, we mean that after first Otsu, we relabel the foreground pixels as 0 and find the threshold on the background pixels. So we keep this resulting binary mask and combine with our second method, which concentrates on the imbalanced histogram between lower and upper half images, where we trim the brightest 10 percentile, as shown with a red line in the image, and apply Otsu on the left of the red line. And then binary masks corresponding to each half image are appended together. And since the double iterated Otsu is eliminated in this method, we reduce the execution time.
Finally, we have to deal with the conveyor belt effect. The bottom section of products have greater glass thickness than other sections. Thus, the bottom appears much brighter than the rest of the body, and this significantly eliminates the conveyor belt grids underneath. That, in turn, causes misclassification of conveyor belt region as foreground, as shown in the below figure. To overcome this problem, we employ marker-based watershed segmentation. The image is segmented into foreground and background regions according to marker pixels, whose scheme is given above, which act as initial water sources to start flooding. We have observed that the output of this method improves with a pre-processing step that we call LPF boosting, where we apply Gaussian blurring to the original ELP image and use the weighted sum of low pass and original images as the input to the watershed algorithm. We combine all these methods to obtain an initial segmentation mask generator algorithm that we call the combined hybrid thresholding, or CHD method. In CHD, we basically treat each of region sampling, two-part histogram trimming, and watershed segmentation as some sort of a weak binary classifier. So we combine their outputs to achieve better accuracy. Also, for thresholding related approaches, we apply post-processing steps such as false positive elimination at background and hole filling at foreground to minimize the error introduced in binary classification with thresholding. An input-output pair of CHD can be seen on the right of the slide. To further improve the binary masks obtained from CHD method, we employ an active contour or snake approach to get a smooth contour of the product. Contrary to the usual utilization of gradient magnitude image as an external energy constraint to the snake evolution, we use a distance transform-based approach. Having obtained an initial mask from CHD, we invert that mask and take its distance transform. This is followed by a pixel-wise negation, where we subtract each pixel from 255. Finally, this negated distance transform image is bitwise ended with the original inverted CHD mask to prevent the snake from stretching into the foreground. We call this procedure as a negative distance transform. The initial contour points required for the active contour algorithm are obtained from the contour of the morphologically dilated CHD mask. These points are polar sorted and then decimated, downsampled with a factor of 5, which grants us with the ability of low pass filtering and smoothing the imperfections of CHD. After a fixed,
please, because you have less than 1 minute.
Okay. After a fixed number of 10 iterations, we label the closed region defined by the linearly interpolated final contour points as foreground. Here on the left, we see an initial CHD mask with imperfections at its neck. At the middle, we see the snake evolution of this product image. And finally, on the right, we see the final binary mask, which is the output of the segmentation block, and the improvement is seen and visible and significant. From the start of localization to the end of segmentation, it takes approximately 138 milliseconds on average per product. This satisfies the timing constraint of our system, and the evaluation metrics indicate that the segmentation procedure has high accuracy. The next step from here is to develop algorithms for defect detection. The importance of the studies on hot-end quality control stems not only from the environmental friendly contributions of such systems to the production process, but also from economical considerations. Hot-end systems in the industry are heavily monopolized by a few foreign companies, which charge glass factories with high fees, both at first purchase of their system and for later annual maintenance. We are motivated by the possibility that our work paves the way for development of viable alternatives to those solutions, with lower economical implications and more freedom in terms of open sourceness. Thank you all for listening.
Thank you for this nice presentation. Your work is really interesting and impressive, I should say.
Thank you.
And do you have any questions? By the way, you can write your questions to YouTube live chat part. Okay, let me see if we have questions there. Any questions from our participants? Okay, let me ask, are you working in a project or did you come up with this idea? Are you making a project with a company like Şişecam or?
Yes. Yes, we are included in a project with a company, and their name shall be not be said for
it's
their
confidential.
request.
Okay, I got it.
Yeah,
it's
confidential.
Really,
yes.
It's really good. Are you gonna apply for a patent application or something like that?
After some development and on-field application, and with sufficient success, yes, with the help, we will probably ask for apply for a patent for the help of the company and for their name, of course, not for us.
Of course. Okay, we have a question from Murat Hoca. He is asking for further information on this conveyor belt effect. Can you please go over that part of your presentation?
Okay. Berkay, you can
very quickly.
All right, very quickly. Just briefly, the glass thickness causes a high radiation in SVR band, and the bottom of the products, the bottom of the products have very high glass thickness, and therefore they appear very bright in the camera, the images. And due to the radiation, the conveyor belt grids that the products moving on are heavily illuminated, and this grid structure makes it hard for this thresholding algorithms to separate between the bottom of the product and the conveyor belt. And the conveyor belt are included in the foreground with the when we use segmentation. But on the other hand, watershed segmentation helps us eliminate this problem with its ability to flood pixels. And yes, I think that will be enough for an answer.
Yes, in this slide, you can see a raw image where we have the grid effect clearly visible. And in some cases, we have more bright products where this problem is even more apparent. This is, I guess, a good product or a typical case.
Thank you very much. Keep going. Way to go, guys. Okay, thank you for this presentation.
Thank you.
Now we will proceed with the next paper, and our next presentation will be held by İlkyaz Biber, Hamdi Kılıç, and Dila Özvardar. They are students from Istanbul Bilgi University, and today they will talk on their work on embedded system design for autonomous mobile exploration and mapping. The stage is yours. Could you please share your screen and start the presentation? Okay, we can see it. Thank you. You can start.
Okay. Hello, dear professors. Today, Dila, Hamdi, and I will going to present our project, which is embedded system design for autonomous mobile exploration and mapping. Here you can see our main titles. In this presentation, we will briefly explain the algorithms that transform high-level human specifications into low-level instructions of how to move, A-star algorithm, properties of an image to draw a 2D map, hardware system of the robot, and lastly, we will show our robot's test results. Mobile exploration and mapping robots can be used to extend human exploration capabilities by providing safe access to hazardous environments or unsafe structures. Thus, as they minimize the risk of injury, they contribute to solve our problems in terms of speed and efficiency. The main purpose of this study is to design a robot with high precision by utilizing a minimum number of low-cost components and set up an effective pathfinding method by drawing a 2D map of the previously unknown environment. Thus, the robot can move to the desired target by using the shortest path, whereas A-star algorithm benefit from the cost calculation method. Learning maps, modeling a previously unknown environment, and set up an effective pathfinding method are major research areas in the robotics community, covering various technical fields such as mechanics, electronics, and computer sciences. But how mapping and pathfinding are related to each other? The creation and updating of the map depends on the measurements that the robot collects from the camera. According to the incoming obstacle data, path can be created in this project. In this project, the robot can move without hitting the obstacles by following a projected path. Further information will be explained in the relevant parts.
Image processing algorithms were the basis of this project. In this project, image processing operations started with taking the live video from the camera. Afterwards, the pixel values of the captured live image were processed and the video stream was switched to grayscale. The reason for applying this process was that instead of processing the images in 3-channel RGB value, it was desired to process them in a single-channel grayscale. The 640 by 480 pixels taken from the live image and integrated into the grayscale, it were converted into a 2D array of the same size. Then a threshold value was given to the pixel values in this array. This threshold categorized pixel values in the range of 0 to 255 into 2 groups. After this categorization, values greater than 127 were processed on the array as 0, and values less than 127 were processed as 1. The easiest way to separate an object in an image is to take advantage of color differences. In this project, a color detection algorithm was used to determine the position of the robot. With this algorithm, the red region placed on the robot was distinguished, and the position of the midpoint of the robot on the map was determined. In this algorithm, firstly, the tone of the red has determined. The color range corresponding to red has identified as a low limit and a high limit, as you can see the percentages in the graph. With this code, the red color range will be known by the algorithm. After that, by red masking, the algorithm scans the spots on the image, and which are categorized as red by their pixel RGB values. When the algorithm detects all the red spots, it unites all of them and applies the dilation filter for filling the gaps between these spots. Right after filling the gaps, the gained area's edges are contoured for finding the area of the place. When all the steps done correctly, by taking half of the height and width of the area of the red shape, the midpoint has been taken. A star is the most popular choice for pathfinding because it is fairly flexible and can be used in a wide range of contexts, and it is often used for the common pathfinding problem in applications such as video games, but it was originally designed as a general graph traversal algorithm. It calculates the shortest path between a given node as a starting point and a goal node as an ending point to reach. Also, the A-star algorithm uses the occupancy grid mapping technique for mapping part. Grid-based maps are created by dividing the environment into certain proportion of pieces. Each cell in the grid holds an information about the environment. This information is usually consists of probabilistic characters that indicate whether the cell is full, empty, or undiscovered. For finding the shortest path between 2 points, A-star algorithm benefits from the cost calculation method.
Cost calculation method works like a loop, shortly iterates itself. Thus, algorithm scans every possible unit of path by the values of functions fn, gn, and hn. The iteration goes by extending the path, increasing one at a time, and the loop stops when there is no possible move on the path. In a detailed manner, fn function is the final value of a unit on path, which consists of gn and hn. That means fn function is the sum of the gn and hn values. Gn function is the cost of moving from the starting point to a certain square on the grid. The Gn function has one unit cost, and it only calculates the differences. But using only Gn function is not enough to defining the minimal path. So the Hn function that calculates the expected cost of path is needed. Thus, in each iteration, the node which has the lowest fn function value is removed from the priority queue. By choosing the highest fn value, A-star algorithm tries to minimize the path.
Here we can see tables created in order to provide the required movement for robot, for left and for right. In the setup phase, 48-watt LED lights were used to make the image clearer, and these are two pieces. Using an Android device, the image taken from the camera of that device. The camera is placed at 90 degrees with an eagle's eye view. The white base is formed with the short side 168 centimeter and the long side 207.9 centimeter, and obstacles are perceived as black. On the robot, a distinction was made by putting the color red. The data received by the robot's HC06 Bluetooth module directs the robot's movement. In order to understand the rotation angle, there is a gyrosensor named MPU6050. Throughout this data, the motor driver understands how long in which direction the motors will drive. The 1000 milliampere 7.4 volt lithium-ion battery has a sufficient capacity to run the system. Communication in our hardware consists of three parts. There are Wi-Fi station, Bluetooth sections. The Wi-Fi section communicates on the same IP address and over the 802.11n standard. This standard operates at 2.4 GHz. Likewise, the Bluetooth section works at 2.4 GHz. The image from the camera comes to the router via Wi-Fi, and the router acts as a bridge and sends the image to the ground station. Here, the data received from the algorithm sends commands to the mobile exploration robot via Bluetooth.
Optimization performance, motion of the robot, efficiency, mapping, pathfinding algorithm, feasibility, precision, and stability demonstrated by means of tests, as you can see in the video. For more accurate results, we perform more tests and run simulations in multiple environments where the robot succeeds to reach its target and avoids obstacles in any situation, as you can see in the video again. Also, increasing the accuracy of a 2D map developed by field vision and image processing. We present methods that combine the strengths of these various approaches. Thus, with the help of these tests, the robots can explore the environment with enhanced stability and increased efficiency. In this work, we propose several algorithms, but most significantly an A-star algorithm that benefits from the cost calculation method. In each iteration, by choosing the highest FM value, A-star algorithm tries to minimize the path. After considering all the conditions, a roadmap to act on is revealed by the A-star algorithm. And this way, we guarantee that shortest path without having the processes any node twice. Thus, the robot can move without hitting the obstacles by following a shortest projected path without the need for any pre-exploration processes. As a conclusion, through these proposed methods, this work has been completed with a degree of success. Hence, this work will demonstrate that robots can improve the overall mapping performance. Besides, we believe that this project should be developed more by following the technology. Required features or qualifications can be added to projects according to the need of users. For instance, we will use robot location feedback mechanism to minimize the errors. Also, additional enhancements in this project will involve a camera on top of the robot to make this project for hazardous environments or unsafe structures where humans cannot enter directly. In this slide, you can see our references, and thank you for listening us. Also, we would like to express our most sincere thanks to our supervisor, Dr. Baykal Sarıoğlu. Thank you for listening again.
Thank you for this nice presentation. Do we have any questions from the audience? Any questions? You can write your questions to the chat box. Okay, if not, I have a question. Can we check again the slide 9? Maybe you can reshare your presentation. I can't see the presentation.
I'm sharing again.
Okay. Okay, on this slide you have a table, but maybe I missed it. I didn't get the idea here. Maybe, yeah, can you go over it very quickly again, please?
This is the deciding mechanism, actually deciding algorithm of the robot for turning ways.
So it is checking the previous x value with the next x value, right? The next x value is the desired point, right?
Yes.
Yes.
And what does stable mean here?
Stable
didn't.
means no change before and
Oh, okay, I see. I see.
one.
Okay, okay, thank you.
You're welcome.
Any other questions? Did you try other algorithms? You mentioned that you had proposed some other algorithms, but you get the best results with A-star. Do you have any results with the other algorithms? Or how did you decide that this is the best one?
We tried with others, but the best accuracy was with the A-star algorithm. We actually run our algorithm, but it was not like that.
Okay, I see. Thank you very much. Thank you. Oh, we have a question. Here you have okay. Serhan Hoca has a question.
Actually, it is a
No.
question, but there is a small delay between YouTube video and our live broadcast. That's why I wait a little bit on the YouTube channel. And this is Dr. Murat's question, Professor Yeşim. That's why I just conveyed to you.
Okay, thank you very much. Here the question is, can the pathfinding algorithms be easily adapted for the camera on top of the robot case? So right now you have a camera attached to I don't know, to the ceiling, right? Can you can you attach the camera on top of the robot?
Yes, we can. First, we try to put the camera on the robot first, previous parts of the project, but then we decided that it will be better if we put the camera to another place and observe all the area, all the environment. That's why we separated them.
Okay, thank you very much. Thank you. Now we will continue with the next presentation. And the next presentation will be held by Ecem Nur Duman. Ecem Nur Duman is a student, I think. Did you graduate, Ecem? Not yet?
No, hi, no. I'm a sophomore physics student.
Okay, yeah, he's a student at Yeditepe University, and today she is gonna talk about the magneto-optical trap and its application in atomic interferometers.
Yes, thank you so
Ecem,
much.
you can start. The stage is
sure. Thank you so much. Hello, everyone. Again, my name is Ecem Nur Duman. I'm an undergraduate physics student at Yeditepe University, and I'm also an undergraduate researcher at Özyeğin University. I work on called Atom Project supported by TUAC, and today I will give you a presentation on the subject of the project. This is the outline of the presentation. This will be as follows. First, I will give you a brief introduction to magneto-optical trap, and then I will talk about the theoretical background of this method, where I will be covering the laser cooling, Doppler shifting, magnetic field, and Siemens Effect. After that, I will talk about the experimental part of the setup, which contains ultra-high vacuum system and magnetic coils. And following that, I will talk about the atomic interferometer devices and how we can use magneto-optical trap in these devices. And finally, I will conclude my presentation. Atoms are very fragile things, so their high velocity and erratic thermal motion make it really hard to work on them and learn more about them. So what we can do about how we can overcome this problem? Slowing down the atom means that you need to decrease its temperature, so which means cooling down the atom. And there are several ways to do that. But the idea of using lasers to cool and trap atoms first claimed by various group of scientists in 1975. And one of the apparatus we use this technique is known as the magneto-optical trap, as you can see on the right-hand side figure. This is the main body of the magneto-optical trap setup, and we can divide it into two sections, which are first part is the laser beams that we use in order to slow and cool down the atoms. There are six laser beams and they are orthogonal to each other. And the second part is the magnetic field that we use in order to trap the atoms at the center of this glass, which is this glass is our vacuum chamber. And I will briefly explain, of course, during the presentation in detail. Why do we need this? Well, it gives us the opportunity to gain a better knowledge about the inner structure of atoms. And after we learn more about them, we can use and manipulate them in order to create novel technological devices such as quantum computers or atomic interferometers. And atomic interferometer part will be discussed during the presentation as well. Theoretical background. So how we cool the atoms, cool down the atoms by using lasers. In magneto-optical trap, we use Doppler cooling. But before we dive into Doppler cooling, there are a few phenomena that we need to cover in order to understand this phenomenon. And the first one is the stimulated absorption. So what it is, Well, the thing is, atoms can shift between two energy states. And in order, by absorbing the photon, and in order to shift there is only one rule here, and it is that the atom can only absorb the equal amount of energy, the difference between these two states. So this is known as the stimulated absorption. And after the atom get absorbed and get excited state, since the excited state is unstable, it will go back to its ground state. And this is by emitting a photon, and this is known as spontaneous emission. And during these interactions, photons are also imparting their momentum to atom and push them back. So we can think about as I mentioned on the last page, there was a figure, there are 6 laser beams that we use, they're orthogonal to each other. We send them each direction, and when we put the atom, they just, there will be some cycles, these absorption, emission, and kicking cycles. And this way, eventually, the velocity of atom will decrease, decelerate, and then we finally slow down the atom successfully. And this is how actually a modern optical trap holds atom at the intersection of these laser beams. However, atoms are not always rest. Everything is fine for the atom at rest, but since it will feel the force equally from all directions. However, when the atom is not stable, let us consider an example on the right-hand side. It's much more different. We need to cover a Doppler shifting phenomena in order to how it works. So let us say there is an atom moving to towards the first laser beam, and there are 2 laser beams that are opposite descend opposite direction, and they have their frequency tuned to slightly lower than the excited state. And when the atom moves towards the first laser beam, it sees its frequency red or blue shifted. This is basically known due to Doppler effect, and this is Doppler shifting. So what happens is when it moves towards the first laser beam, it sees its frequency much higher than its initial frequency, which we call omega 1. What about for the second laser beam? Since it moves away from the second laser beam, it sees frequency slightly lower than its initial frequency. And this will be the final situation for the laser's frequency. And as you can see, the first laser beam's frequency is very close to excited state that can atom absorb. And this way, if we go back to beginning, we can reach this cycle with, of course, unstable atoms as well. And by during the cycles, it slows down, and this cycle is known as the Doppler. And for the magnetic field, well, laser pulling is a great method to slow down the atoms, but it's not strong enough to trap them and concentrate them in one location. So we need external magnetic quadrupole field. And the properties of this magnetic field is basically at the center of these coils, the magnetic field is 0, and it increases linearly when you move away from the center. And this 0 point field, we call that 0 point field, will be the place where we're going to trap the atoms. And what we also observe when we apply magnetic field is the Siemens Effect. It's another phenomenon which is splitting of an atom's energy levels due to the interaction of the magnetic field. And these are the energy levels. As you can see with this splitting, the atoms can absorb light with a greater probability and with requiring less energy levels. So it makes it easier to shift between 2 energy levels. And this is another phenomenon that we observe. For the experimental setup, there are 2 main parts, magnetic coils and ultra-high vacuum system. So what is ultra-high vacuum system? So ultra-high vacuum system basically means that you have lower pressures. And what is the meaning of low pressures? You have less amount of atoms and molecules inside your chamber or system. And this vacuum chamber is solid enclosure from which vacuum part moves air and the other gases. And why do we need this? Well, as I mentioned, we are trying to trap the atoms, and there should be a pure interaction between the atom and photon. So we don't want any contaminants inside the chamber that can just blow this up, blow this interaction, or any molecules or atoms can knock out the trapped atoms. So that's why we need actually ultra high vacuum conditions, and which have 2 properties: clean environment and low pressure. And low pressure means basically for ultra high vacuum setup is 10⁻⁷ Pascal or much lower than that actually. On the right-hand side, you can see our diagram of our setup. There is a different types of vacuum pumps that you can use in order to reach lower pressures. We're going to use first surfing pump, then turbomolecular pump, and then the ion pump. However, unfortunately, these types of pumps are not enough to maintain or reach the low pressure level that you needed for your system. So we need additional operations like cleaning and baking up your system like up to 400 or 300 Celsius degree. And this is the place, this is the chamber where we're going to trap the atoms. Magnetic coils. So as I mentioned, magnetic quadrupole field is needed in order to trap the atoms. And this on the right hand side, you can see the diagram of the magnetic coil. These are basically two coils that we run a current in opposite directions so that they can cancel each other at the center. And this is the configuration of anti-Helmholtz coils. That's why we call them an anti-Helmholtz coils. And this is the 0 point that I mentioned. This is the place where we're going to trap the atoms. And these are the laser beams, 6 laser beams that are orthogonal to each other. And this is the schema of the magnetic coils and how we can measure the magnetic field produced by these coils by using this equation where this is a constant absolute permeability of free space and number of turns of the coil. I is the current flowing through the coil, R is the radius of the coil, and X is the distance of the point from the center of the coil. And for our experimental setup with the 2 ampere current, 200 turns and 0.05 meter diameter, and 0.04 meter distance from the center, we can theoretically produce 15 Gauss, which is reasonable value in order to trap the like approximately 10 to the 6 or 10 to the 7 atoms. So atomic interferometers. Atomic interferometers, their high precision and sensitive measurements makes them really great devices and great tools to use many applications, ranging from inertia sensors to space exploration and military mission, etc. So, but how does it work actually? Well, before we dive into how atomic interferometers work, let us consider just how interferometers work. Basically, they are just using light instead of using atom. And one of the most common popular interferometers for light is just the mass sender interferometer. And how does it work? So basically, you send a laser beam and then split it by using beam splitter. And let's say this is the first laser beam, and this is the second laser beam. And we apply external effect, the first laser beam, so that there will be time delay. And then we combine these 2 laser beams again by using beam splitter and detect it. And then what we see on the screen will be the interference pattern, dark fringes, light fringes. And basically, by looking at by analyzing this phase shifting, we can learn more about what happened or what was the interaction on this path. So this is how it works. And actually, the atomic interferometer works like the same like mass sender interferometer. We just only use launching of launch a cloud of cooled atoms into free fall. In detail, the working principle of atomic interferometers. There will be 3 precisely timed pulses that we're going to send to our atomic clouds. And first pulse, you can think that is a beam splitter on the mass sender interferometer. It will act like a beam splitter, and it just transfers its momentum to these atom clouds, and then put them into superposition of 2 states. And after that, after t time passed, we're going to send another pulse, which just flip the momentum difference between these 2 clouds. And then after t time passed again, we're going to send this third pulse in order to just close the interferometer. And where is the part of the magneto-optical trap? Where, as I mentioned, we have a cold cloud of atoms. And how we can prepare this? Well, one of the ways that we can do this is the magneto-optical trap. And why using magneto-optical trap allows the atomic interferometer to have a very long interaction period, and which improves the sensitivity. Also, as we talked about, the magneto-optical trap also have ultra-high vacuum system. So we are dealing with the atoms here, so we don't want any environmental distribution on anything. So ultra-high vacuum is a really great opportunity for this atomic interferometer devices as well. And by the way, the result of this atomic interferometers will be like the same with the interference pattern again with the the mass and the interferometer. Conclusion. Magneto-optical trap uses the cycle of absorption and emission, and with the help of the impact of magnetic field, it traps the atom at the center of your system. And it enables us to comprehend the deep structure of, and strange properties of atoms in light. Not only to do that, but also it gives us an opportunity to manipulate and use them in such a great technological devices such as atomic interferometers. And the magneto-optical trap is a very least expensive way to cool down the atoms compared to the other methods. And development of this technological device so important that can be credited to low cost of work is a great deal of work. And all this work that I presented here is carried out in our quantum optics laboratory with the aim of providing advancement in the field of atomic physics to lay the foundation for the production of important technologies as well. And these are the papers that I took advantage of while I was writing the paper. And this was the end of my presentation. This is our research team. Many thanks to all of them. But of course, a special thanks for to my supervisor, Dr. Kadir Burak, and he's here. And my mentor, he's Mehmet Ancu, who also works on this project called Atom Project as well. And of course, thank you for IEEE giving me this chance to present. Thank you.
Thank you, Ecem. This was a very nice presentation, and the idea was very interesting. I learned a lot from it. Thank you for this very nice presentation. Do we have any questions from the audience? I'm checking YouTube chat box. And okay, Jim, maybe I missed it, but did you publish this work in any conference or?
No, Jim, this is the first time, and yeah, this is the first time, and actually it's an experimental work. So mainly the project is mainly just started. So we're just trying to construct the experimental setup, main experimental parts of the setup. So this is actually magneto-optical trap is one of the basic elements that you need in your lab if you're working on cold atom physics. And you can just making atomic interferometer is just only one of the application of it. You can just work on lots of things, and this is just like the main setup for cold atom project. I hope that it will end up with great results. Fingers crossed.
Okay, very nice. And you mentioned that this approach can be used in the development of technological devices, right?
Mm-hmm. Yeah.
Did I get it wrong? Do you have something in mind?
This is the atomic interferometer, actually. It's a device. Yeah.
Yeah, I understand that. Do you have any technology?
Quantum computers. Actually, there is a company called Quanta. I guess it was in America. I don't remember exactly. America or England, I'm not pretty sure. They use magneto-optical trap in order to create quantum computers. And quantum computers are like the new type of computers. I mean, I don't know whether if I go dive into it, but it can just, they are using magneto-optical trap method in order to create quantum computers. This is just for example. It can be also used, atomic interferometers can be used, navigation systems, and making very sensitive measurements and etc. Yeah.
Oh, thank you. Very nice. Very nice. Murat Hocam, do you have a question? Collision of the laser beam of where is the excess energy going? Okay. I got the question now. Murat Hocam is asking of the atom moving towards the laser source accelerates the atom, right? And where the excess energy is going?
The excess energy, like kicking the photon, kicks off the photon. It releases its energy, and that's way it loses its kinetic energy. By these cycles, it's always just kick back and just it loses its kinetic energy, and when the kinetic energy decreases, that means also the velocity of the atom will decrease and its temperature also decrease. So mainly we cool down the atom and slow down successfully.
Okay, thank you. Do we have any further questions? Sorry, I'm checking the chat box. What is the form of the emitted energy?
Form of the emitted energy.
What is the form of the emitted energy?
I don't know whether I get it right, but it emits a photon, like the packets, energy packets, basically. It emits a photon and then get to excited state.
Any other question? No, I think that's it. Thank you. I want to thank you all for this wonderful session. It was really impressive, and the work done presented here was really high quality work. I wish you good luck in your further academic life. Okay, we received another question, Ecem. Maybe you can also answer that one. So this is, how close are you guys to take the photo of a single atom?
Taking photo of single atom. So here is the thing. The magnet-optical trap, I just mentioned actually about this in one place. We just approximately, with a 15 Gauss magnetic field, we approximately trap like 10 to the 8 times 10 to the 6 atoms, which is like far away from a trapping single atom. And trapping single atom is another, you need like, yes, you can do that by using laser cooling. And but you know, with this setup, we need to change some things. I mean, the things that I mentioned, like all the values, all the general idea, we need to change a little bit stuff. And yes, you can make it actually like you can create trap only one atom, but you need also like different. You need to use also different ways. It's not just we can do this by using this. But yes, it can be happen, and yeah, it can be happen, but we need to change some stuff. However, it is possible to make it, but capturing it, and currently this is not our aim, but this was on our mind. I hope we can make it after we have this setup. We can try it.
Okay, thank you, Ecem, once more, and congratulations all. So as I mentioned earlier, the work done is very impressive. So your advisors must be very proud of you. And this is the end of this session. The next session will start at 2 p.m. I wish you good luck and success in your further academic life. Thank you.
Thank you.
Thank you.
Thank you, Yeşim Hocam. And
Thank you, Murat Hocam.
I wish you happy birthday.
Oh, thank you.
It reminded me of this.
So I'm trying to forget it because, you know, I'm 40 now. Anyway.
Hocam, happy birthday.
Thank you, guys. Thank you.
Now we are closing the first session of today. See you at 2 o'clock.